One of the things that I get asked about a lot is how terms like deep learning and subtypes of deep learning tie into other broader terms like machine learning and artificial intelligence. So I've drawn this complicated Venn diagram, and we can spend a few minutes now talking about how all of these terms relate to each other. Let's start on the outside with artificial intelligence, or AI. This is the buzziest, vaguest, and broadest of the terms that we'll be covering. A good technical definition is that AI involves having a machine process information from the environment, and then it factors that information into decisions toward achieving some desired outcome. Perhaps given this, the ultimate outcome or goal of AI would be to achieve general intelligence, which we'll talk about a bit more later. But this is like intelligence as humans commonly refer to it. So whatever it is that we measure with IQ tests. In practice, and in the popular press, the term AI is used to describe any cutting-edge machine capability. Today, that includes things like object recognition with machine vision, voice recognition, question answering, self-driving cars, playing board games like Go, and video games like Atari. Today, deep learning, specifically, is driving the bulk of the progress in the AI capabilities that I just mentioned. So we see the words deep learning and AI used almost interchangeably by the press. Once an AI capability becomes commonplace, for example, recognizing the handwritten digits on envelopes, which was cutting edge in the 1990s, once that kind of thing becomes everyday, the AI moniker is dropped by the popular press for that particular use, and we move on to something else that's even more complicated. All right, so that's kind of what artificial intelligence is in general. Now let's talk about the next ring in this diagram, so machine learning. Machine learning is a subset of AI, and it includes, or it's alongside other aspects of AI research like robotics. So, somewhere else in this Venn diagram, undrawn is robotics. Machine learning is a field of computer science concerned with setting up software in a way such that the software can recognize patterns in data without the programmer writing the software needing to explicitly dictate how the software should carry out all aspects of the recognition. That said, typically the software developer would have some insight or hypothesis into how the problem could be solved, and so would architect the software at a high level such that the software is well prepared and well equipped to solve the problem. Most typically, this kind of preparation involves engineering features. So cleverly processing the data that's being input into the algorithm into something that statistical models can much more easily understand and make inferences from. So a kind of conventional way of thinking about this with traditional machine learning was for any kind of problem like machine translation or computer vision, the people working on those problems would spend about 90% of their time engineering features and only 10% of their time actually running statistical modeling. Let's move one ring further inside now, so into representation learning. We're only going to talk about this for a second at a really high level. So, there's a bunch of different types of machine learning, and a big and an increasingly important part of that is representation learning. So in representation learning, we are writing algorithms that don't require the kind of 90% of your time spent engineering features. In representation learning, you're providing more or less raw data into the algorithm, and the algorithm itself is figuring out how to engineer those features automatically. So instead of the 90-10 split of feature engineering and statistical modeling, with anything under the representation learning umbrella, we're kind of turning that on its head and spending only 10% of our time actually engineering the features, coming up with clever ways to turn pictures or words into features that a machine can work with, and allowing the machine to figure it out for itself. By far, the most prominent part of representation learning is artificial neural networks. So artificial neural networks is this subfield of machine learning and representation learning. And this involves artificial neurons, which are simple algorithms inspired by biological brain cells. And this kind of explaining what artificial neurons are and what deep learning is, we're going to spend a bit of time in this lesson later on going through the key terms. But if you're unfamiliar with any of these key terms or what artificial neural networks are or deep learning is in general, I'd recommend that you check out my Deep Learning with TensorFlow live lessons, which cover all of that in detail. So we'll just spend a minute on it here. The artificial neurons are inspired by biological brain cells, particularly in the sense that an individual neuron, whether it's artificial or biological, receives input from many other neurons, performs some kind of computation, and then produces a single output. An artificial neural network is a collection of artificial neurons arranged together so that they receive and send input between each other. So then deep learning specifically, this is really the simplest of all of the terms here for me to define because its definition is very specific. A deep learning algorithm is an artificial neural network in which the artificial neurons are stacked at least several layers deep. As endless research and competition wins since about 2012 have illustrated, deep learning, provided enough data and processing power, is capable of solving a broad range of problems that were previously intractable. This allows the accuracy of many kinds of AI applications to, whether it's voice recognition or visual recognition, it's enabled those applications to jump from like a 95% accuracy to a 99% accuracy. These are the tricky final percent, and they're the critical few percent that make an automated service feel intuitive and magical. So these capabilities include many of those that I mentioned above, like machine vision, natural language processing, and deep reinforcement learning. Specifically, there are some types of these that we'd like to speak about today. So machine vision in general, we're going to cover that in a few minutes. And we're going to talk about deep learning for natural language processing. We're going to talk about deep reinforcement learning, and we're going to talk about how all of these terms relate to each other. But to give you guys a quick overview of the two key terms that are in the title of these live lessons. So generative adversarial networks. This involves playing two deep learning algorithms against each other as adversaries, such that one becomes incredibly capable of generating real-to-life visual images. And then deep reinforcement learning, this uses deep learning neural networks to discover what actions to take in a particular environment in order to obtain a reward. So if you're having the algorithm play an Atari video game, then the reward is maximizing point score. If you're building a self-driving car, then the reward is getting you to your destination safely. So you provide rewards for safely driving to a particular destination. And with deep reinforcement learning specifically, we use artificial neural networks at some point in the algorithm. And then reinforcement learning is this kind of broader category that's been around since at least the 80s. And so this is similarly discovering what kinds of actions to take in a particular environment in order to obtain rewards, except that reinforcement learning doesn't necessarily have to be deep reinforcement learning. So let's get into talking about these deep learning subsets in more detail now. Introduced in my deep learning with TensorFlow Live lessons were these dense networks, where we use them initially for machine vision applications. We also used dense networks in my deep learning for natural language processing live lessons for classifying documents by their natural language. Dense networks are super versatile. They're one of the conceptually simpler types of neural networks, but don't mistake simplicity for the breadth of their utility. Dense networks enable information to interact and recombine, non-linearly recombine if that's necessary, and they can solve any kind of continuous function. More layers of dense network provide more opportunity for abstraction from the raw input to learn representations of features through those layers and then to produce some output. So to define them specifically, dense layers are any kind of layers in a neural network where all of the neurons in one layer pass information to all of the layers in the subsequent layer. And these kinds of dense layers can be found somewhere or other in the vast majority of deep learning networks. Indeed, dense layers are found in nearly all networks I build in all of my live lessons, including the current ones. So get used to them. Convolutional networks, or convnets for short, CNNs for short, I've got them here on my diagram. They are best known for their use in machine vision applications. We, for example, use them to classify images of handwritten digits in my deep learning with TensorFlow Live lessons. Other applications prominent today include self-driving cars, face recognition on Facebook, or unlocking the Apple iPhone X with your face. Convnets can be useful for any data involving spatial patterns. Indeed, this includes data outside of strictly visual data. So in my deep learning for natural language processing live lessons, we found convnets, CNNs, to be an efficient layer to incorporate into our natural language networks as well. These CNNs are relevant to AI in particular. If the application is going to need to visually recognize objects or navigate a real-world environment, then you're very likely to find a convnet useful there. Recurrent neural networks, or RNNs for short, are specialized for use with data that occur in a sequence. For example, natural language data, like written text, or like me speaking to you right now, that's sequential data. Financial time series data are also sequential. Particularly powerful variants of RNNs include gated recurrent units, long short-term memory units, or LSTMs, particularly bidirectional LSTMs. So these kinds of networks, they were the focus of my deep learning for NLP live lessons, and they're relevant to AI applications if that AI application involves language in some way. So voice recognition, interpreting commands that are typed naturally, or answering questions. Prominent applications today include voice assistants, so Amazon Echo or Apple Siri, Microsoft's Cortana, search engines, between language translation services, including real-time voice translation on phones or on voice computer calls. So these are also a really important class of algorithms. And natural language processing, like reinforcement learning, is this kind of broader category, but we find that these deep learning for NLP approaches have been especially powerful in the last couple of years and have begun to displace the traditional machine learning approaches to NLP. So we're seeing things like RNNs and LSTMs becoming the dominant type of application, of choice in building an NLP program. So now let's move on to one of the particular topics that we're covering in these live lessons. So generative adversarial networks. This is the first of the two main topics that we're covering in these live lessons. The theory for these is only a couple of years old. It's one of the most exciting and quickly evolving areas in deep learning today, and it's one of the topics I'm asked about most, to teach. So these GANs, for short, they're in the machine vision bucket of deep learning approaches, and specifically they create photorealistic images that have never been seen before. So, these could be bedrooms or birds or celebrities' faces, and they can blend styles. So they can start with a photo or a hand-drawn sketch and then convert them into the painting in the style of your favorite artist. Or a winter scene can be converted into a summer one. We're going to talk about more of these examples momentarily. GANs are commonly discussed in AI conversations today because previously, convincing photorealistic art was a human-only pursuit. Some people consider GANs to be creative. However, we've got to remember that they're significantly constrained by the particular data that they're trained on. So I'm looking forward to building a generative adversarial network with you in these live lessons. The other main topic in these live lessons is deep reinforcement learning. If I had to pick a single topic that I think is most fascinating in deep learning, maybe in the world, I'd say it's deep reinforcement learning. So reinforcement learning in general, this involves an agent exploring some environment. So if you're designing a reinforcement learning algorithm to play a video game, you could have your agent pressing the buttons on a video game controller. It doesn't actually hold the controller in its hands, but it's the same kind of idea, controlling the actions of the player on the screen. If you were building a self-driving car, then your agent would be steering the wheels and pressing the gas and the brake pedals. So these actions have an impact on the environment, whether that's the character on the Atari screen and the environment around the Atari character, or the world around the self-driving car. The agent is trying to take optimal actions within its environment, but because it's taking these actions and its actions are affecting the environment, it makes it a very complicated task. So the actions that will lead to accumulating the most kinds of rewards. So we have to decide as the humans building the deep reinforcement learning algorithm what kinds of rewards we want to have. But the algorithm will try to maximize these rewards in some way. And if in the Atari game example, this could be just trying to maximize point score. If we're talking about a self-driving car, going back to that example, we can reward points for a safely traveling distance toward a destination. So we're going to get into way more detail on reinforcement learning and deep reinforcement learning specifically in these live lessons. So that kind of introduces reinforcement learning, this whole bubble. But how about deep reinforcement learning? Well, the definition here is relatively simple again. This can be defined as any type of reinforcement learning algorithm that incorporates artificial neural networks, deep learning networks, to optimize some aspect of the algorithm. While the theoretical foundations for the deep reinforcement learning idea have been around for a couple of decades, in the past couple of years, deep reinforcement learning algorithms have been taking the world by storm, thanks to exponentially larger data sets, parallel computing across many graphic processing units, GPUs, to crunch all of these data and the possibilities that they generate, the possible actions and the possible environmental states. And the third thing driving deep RL advancements recently is this quickly developing body of new ideas on how agents can be trained to efficiently identify the optimal actions that they should take in a wide variety of situations. The biggest headlining advances in AI in recent years have all involved deep reinforcement learning. So we're now tying very outside of our whole Venn diagram to deep reinforcement learning specifically. So, these big headlines in AI have involved things like a single algorithm that can outdo human performance on many different Atari games, decidedly defeating the world's best players at the very computationally complex board game called Go. And without any training data whatsoever, deep reinforcement learning algorithms have also handily defeated the world's best chess algorithms. On top of using machine vision, which is why I kind of overlapped the machine vision and deep reinforcement learning bubbles, is we'll often use algorithms like CNNs within a deep reinforcement learning algorithm to recognize objects in the visual environment. So with the Atari example, to recognize the pixels on the screen and figure out what those pixels mean and how to interact with them. In the self-driving car example, this is recognizing objects in the visual environment, pedestrians, bicyclists, other cars, streetlights, stop signs, the edge of the road, that enable self-driving cars to figure out what the right actions to take on the road are. Of all of the topics in deep learning, it's my opinion that deep reinforcement learning is probably most closely tied to the popular perception of artificial intelligence as a system for replicating humans' cognitive capacity. To understand this better, let's take a moment to discuss the categories of artificial intelligence. So, artificial narrow intelligence, this is expertise on a very narrow task. We have this today in a few different domains. So for example, the examples we already discussed, visual recognition, machine translation, algorithmic financial trading systems, playing board games, playing video games, self-driving cars. These are examples of narrow intelligence. The self-driving car algorithm is going to be no good at playing the board game of Go, for example. Artificial general intelligence involves a single algorithm that could perform well at all of the tasks just described. So an AGI could simultaneously be a great machine vision algorithm, a great natural language task algorithm. It could make financial decisions. It could play board games. It could drive a car. Sounds a lot like you and me. So this is an algorithm that is approximately indistinguishable from all of the cognitive capabilities that you and I have. There are so many hurdles to achieving AGI. We'll discuss these at the end of these live lessons, that it's probably impossible to guess when it could be achieved, if at all. That said, in a 2013 study by Vincent Muller and leading futurist at Oxford University, Nick Bostrom, they asked hundreds of professional AI researchers when they thought AGI would occur. The median guess was that we would have AGI in the year 2040. Third, and finally, is artificial superintelligence. So this is difficult to describe because it's mind-boggling to comprehend, but this is where an algorithm that is unquestionably more advanced than cognitive capabilities of humans arises. So if artificial general intelligence is possible, then perhaps artificial superintelligence is as well. Of course, there are even more hurdles in the way of ASI than AGI, most of which we can't imagine today. We can't foresee them. So using that same Muller and Bostrom survey as a complete finger in the air estimate, AI experts estimate that ASI could be attained by the year 2060, which could very well be in our lifetimes. What an exciting time it is to be alive. And what an exciting topic that you're interested in with deep learning and deep reinforcement learning, given the relationships to these broad ideas. As we'll see when we demystify generative adversarial networks and deep reinforcement learning algorithms by building our own during these live lessons, Today's algorithms are exceptionally narrowly tied to particular problems. We certainly won't be seeing AGI or ASI in the next few years. But these advanced deep learning topics may serve as part of the future of the foundation of AGIs or ASIs. For now, there's one thing I can say for certain. Generative adversarial networks and deep reinforcement learning algorithms are really cool and really powerful on the narrow tasks we apply them to. I can't wait to show you in hands-on code demos as these live lessons progress.